So I'm going to very quickly try to cover a lot of material related to both imaginary numbers and complex imaginary numbers. I want to start with something that we probably all can solve. We can add the opposite to both sides and get 9. We take the square root of both sides, and it's either positive 3 or negative 3, because negative 3 times negative 3 will give us the 9 that we need in the original problem, such that 9 minus 9 equals 0. Another way we could have solved this here is we could have done x minus 3 times x plus 3, because this is a difference of squares, and actually kind of understanding that this form, that middle term cancels out, will become very important later. So if we were to solve it this way, we could say, well, that means either x minus 3 has to equal 0 or x plus 3 has to equal 0, which means my answers are either 3 or negative 3. Either way, same answer. All right, those are real answers. And when we say real, it doesn't mean that these other things that we're coming with don't really exist, even though they're called imaginary. But they are a part of the real number set, which includes counting numbers, it includes negative numbers, it includes rational numbers or fractions, and it includes irrational numbers like square root of 3 or square root of 5 or pi. So those are all included in the set of reals. If we were to change this problem slightly and make it x squared plus 9 equals 0, you can kind of see at the beginning, oh, that's going to be impossible because there's nothing that we can get there. But let's go ahead and solve it. So we subtract 9 from both sides, we get this. We take the square root of both sides, we get this. Now, I'm not going to put the plus or minus out front. You probably should, but just for now, let's not. Let's just say we're looking for the positive square root. Occasionally you will get a problem that just looks like this, and that usually assumes you are only looking for the positive square root. If I want to put the plus or minus out front, I could, but I'm going to keep it simple for now. So we're like, well, that's square root of negative 9. If I actually take square root of negative 9 and plug it in the original problem, that actually is the answer, because if we square a square root, those are inverse operations, so that'll be negative 9 and 9. So this is actually an answer. It's not an answer that we're used to, and we don't actually know what this thing is because it doesn't exist in the set of real numbers, but we're going to invent another set of numbers, which are going to be called the imaginary numbers. So we're going to say, well, in the same way that I can break apart anything underneath the radical, I can break this apart into factors and say, well, that's 9 times negative 1. I know how to take the square root of that. It is 3. And that's negative 1, so that's still an equivalent answer. And then I'm just going to say, well, we're going to come up with this answer a lot. I don't want to be writing square root of negative 1 all the time. I'm going to call that I. And that's going to stand for an imaginary number. This is maybe misnamed. Maybe it should be called the negative square roots or some other clever name that you can come up with. But we call it the imaginary numbers. And I like to make the point that just because this answer is part of the imaginary set of numbers doesn't mean it's not an answer that is valid. It is not an answer that is in the set of real numbers. And sometimes that real and imaginary, we think about them as if one really exists and the other doesn't. The other exists but in a different framework. Okay, quickly moving on. The imaginary unit is square root of negative 1. So if we square it, that is square root of negative 1 squared. These two are inverse operations, so they cancel each other out. So that means I squared is actually just equal to negative 1. Okay, that seems a little weird, but it works. Okay, I to the third. That is basically the same as I squared times I, which means we already know I squared is negative 1, so that's negative 1 times I. So we know that I to the third is actually equal to negative I. A little strange, but that's what happens. Okay, I to the fourth. Okay, this is basically I squared times I squared. Well, we already know I squared times I squared is negative 1 times negative 1. So I to the fourth is actually equal to positive 1. I to the fifth. Well, this is basically I to the fourth times I, which means we are back to where we started, and this pattern will continue. So something to think about. Oh, I didn't show you that last part. There we go. Moving on. All right, we're going to talk about complex imaginary numbers. Sometimes we'll just call these complex numbers. And what they consist of is some real number plus some coefficient that's real and an I. So it's going to usually have both a real component and an imaginary component, and we call it complex or complex imaginary numbers. If I put something into the quadratic equation, like x equals -8 plus or minus square root, let's just say this was a result. I've already evaluated most of it over 2. This normally we'd say, oh, this doesn't have a real answer, and that's correct because it has a complex imaginary answer. So that's going to be x equals -4 plus or minus square root of -4 is, square root of 4 is 2, and then square root of -1 is I, and that's all over 2. So basically that's -4 plus or minus I. So I've got my real component, and then I've got, there's a 1 in front of there if I want to think about that, but there's my imaginary component. And then you could also write that, you could break it into pieces. You could say -4 minus I, or x is equal to -4 plus I. And those are both solutions to that quadratic equation we had set up. All right, moving on. Addition and subtraction. This is pretty straightforward. We just treat these almost like they're, if you wanted to think about an analogy, if you had rationals and irrationals, if this was 3 square root of 3 and this was 2 square root of 3, we could combine those like terms with those same square roots, and then the rationals would be added together. So in this case, the 2 and the 4 are going to go together, and the 3i and the minus 2i, and I probably didn't need that step. I probably could have gone straight to 6 plus I, or 1i if I want to write it that way. Except did I get everything right there? I did. In my notes I wrote it wrong. This one right here, same thing. The only trick here is some people forget that minus affects everything in there. So I'm actually doing -8 and then a minus I. That negative gets distributed, flips all the signs inside there. Otherwise, it's the same process. -7 and -8 is -15, and 4i and negative I is 3i, positive 3i, and in that case my notes, I've got it correct. Moving on. I think we're going to make it under 10 minutes. So at any point, you might want to freeze this and look at this, and you also might want to try some of these problems ahead of time. Okay, I'll get that on the screen in a minute. Multiplication. We FOIL this out. Okay, there's only one unusual thing that happens. So 7 times 8 is going to give me 56. 7 times 3i is going to give me 21i. I times 8 is going to give me 8i. And then 3i times I is going to give me plus 3i squared. Except 3i squared, I can simplify. So this is 56. And these two combine to 29i. I'm hoping I'm not making any errors here. And then 3i squared is going to be 3 times -1, or -3. So -3 and the 56 will make 53 plus 29i. That's my solution. And so that I squared becomes a -1. And then those are both real numbers now. So that's kind of cool. Those, when you multiply two imaginaries, if they're both just I, they become a real number. Okay, this is the part that's going to be really important. When you have a number, this looks a lot like our difference of squares from before. These are called conjugates, or sometimes complex conjugates. And anytime I have my real parts the same and my imaginary parts the same but opposite, something magical happens. Okay, so what's going to happen? Well, you should already kind of know what's going to happen based on what happened with our difference of squares. But the 2 times the 2 is 4. 2 times the 3i is 6i. -3i and 2i is -6i. And then -3 and positive 3i is going to be a -9i squared. And my middle terms cancel out, as I should have expected. And then I get 4, and then -9 times -1. So that becomes 4 plus 9, or 13. Anytime I multiply two complex conjugates, you end up with a real number. So that's kind of cool. Last step, all the way to division, just slightly under, we're going to be under 11 minutes. I should be able to upload it. Okay, just like we don't like to have radicals in the basement, in the denominator of a fraction, we don't like to have i's in the bottom. It's kind of like having a root in the bottom. So to get rid of these, we're going to use our conjugate trick. So I'm going to say, oh, if I multiply this times 3 plus 4i, which is the conjugate, I'll have a real number under there. So I just got to multiply the same on the top. Anytime I convert a fraction, I got to multiply the top and bottom by the same number so I don't change the fraction. So this kind of doesn't even turn into division. It's really kind of a multiplication problem. So these are FOILed out. I can put parentheses around them if it makes you feel better. So I'm going to get 24 at the top, 32i, 6i, plus 8i squared, all over 9, plus 12i. Now I could probably skip this step because I know those are going to cancel out. So I could just say, okay, that's going to be a minus 16i squared. So this further simplifies. That's a negative 8. I'm going to go ahead and combine it here because I'm running out of time. Negative 8 plus 24 is going to be, if I can do that, 16. 32i and 6i is going to be 38i. And finally, those cancel out. My negative 16 times I squared, that's a negative 1. Negative 1 times negative 16 is positive 16. 16 and 9 is 25. If I want to break this apart so it actually looks like it's in complex imaginary form, if these fractions would reduce at all, I would reduce them. In this case, I don't believe they do, and we are done